Hello and welcome to our webinar on vibration isolation bearings. Today I'll be taking you through the following topics. You may have read our Building in Noise Reduction white paper, which detailed how vibration isolation bearings, strategically placed within buildings, can reduce the effects of noise throughout. This webinar session is designed to give you more information about isolation bearings and how to get the highest performance from them. Specifically, we will take a deeper look at natural rubber versus steel bearing designs. Before a bearing is specified, an acoustic consultant assesses the site to establish the severity of the ground-borne vibrations caused by trains and heavy vehicles. If it's considered that the proposed building would benefit from an isolation strategy, the acoustic consultant will establish the maximum natural frequency for the bearings. Before we study the relationship between a building's isolated natural frequency and the ground's disturbing vibration frequency, we'll explain what is meant by natural frequency. The natural frequency of a body supported by a spring is related to the vertical dynamic stiffness of the bearing and the mass of the body. Natural frequency is measured in hertz, or cycles per second, dynamic stiffness in newtons per metre, and the mass in kilograms. The dimensionless term, transmissibility, is used to define the level of attenuation or reduction of the disturbing vibration amplitude passing into the structure. The transmissibility, T, equals the vibration amplitude of the isolated building just above the bearing, divided by the vibration amplitude of the ground just beneath the bearing. For a perfectly linear elastic spring without any damping, the expression for T is this, where F is the lowest dominant disturbing frequency of the ground-borne vibration and Fn is the natural frequency of the bearing. Due to the damping inherent within all elastomeric materials, the expression for transmissibility is modified to take account of damping. We will not go into detail about that today. This figure shows the vertical axes as the transmissibility on a logarithmic scale. The horizontal axis is the ratio of the forcing frequency from the ground vibration divided by the bearing's natural frequency and is referred to as the frequency ratio. To achieve isolation, the transmissibility value must be less than 1, which occurs at a frequency ratio of 1.41, the square root of 2. If the frequency ratio is less than 1.41, then the bearing will amplify the ground vibration through to the building, which is clearly highly undesirable. The peak transmissibility response occurs when the natural frequency equals the dominant disturbing vibration frequency. It is therefore desirable to increase the frequency ratio well beyond 1.41 to reduce, or attenuate, the vibration energy passing through to the structure. As an example, if the ground's dominant forcing frequency is 30 Hz and the natural frequency of the bearing is 10 Hz, giving a frequency ratio of 3, the transmissibility will be about 0.1, meaning that the ground vibration amplitude will be reduced by about 90%. The incorporation of internal reinforcing plates in rubber bearings increases the load that can be supported for a given bearing plan area. The steel plates, which are bonded to the rubber, restrain the tendency for the sides of the rubber to bulge under load. For a given elastomer modulus, we calculate the bearing stiffness by manipulating the rubber layer thickness, the number of rubber layers, and the shim plate plan area. When calculating a bearing static stiffness, we must satisfy the requirements for stability of the bearing under the applied load and keep the rubber strains below a maximum permitted level. The bearing's dynamic stiffness, which is used in calculating the natural frequency, is greater than its static stiffness. The small strain dynamic stiffness of the rubber compound is much greater than the large strain static stiffness. Non-linearity arising purely from a bearing's geometry is significant, though much of the stiffening typically seen in a static force deflection plot arises from the lead-in associated with the slight misalignment of the bearing faces. For natural rubber, the effects of frequency are quite small. The ratio between dynamic and static stiffness is termed the dynamic to static ratio. The most appropriate means of establishing the dynamic stiffness from a static load versus deflection curve is to take the tangential stiffness at the working load. With this definition, we find that the dynamic stiffness ratio is typically 1.4. So with a clear understanding of the relationship between the bearing's static and dynamic stiffnesses, we are able to generate a plot of the bearing's natural frequency versus its static deflection. This information is useful in establishing the level of vertical movement the building will experience due to the bearing's deflection. Bearings designed for high isolation performance have a low natural frequency, may need to be pre-compressed to about 80% of the working load before delivery to site. This will significantly reduce the vertical movement experienced by the building during construction. As the distribution of the building's mass varies across its plan, each bearing location must be assessed on its own merit to ensure they all deflect evenly when supporting their designated loads. The loads from one location to another may vary by orders of magnitude. This important approach to bearing design will prevent unnecessary stress to the building structure and will ensure all bearings deflect by the same level. So whether it's a 10-ton or a 1,000-ton bearing, both should achieve the same deflection at their working loads. At the high-performance end of bearing isolation, consultants are currently being led to believe that rubber bearings cannot deliver a low natural frequency, but this is wrong. The industry is being misinformed about the capabilities of rubber bearings. With the correct manufacturing controls in place, it is certainly possible to achieve a natural frequency with rubber bearings of 3.5 Hz and below. Rubber bearings offer the advantage of a small amount of intrinsic damping. Although damping slightly reduces the degree of isolation, some damping is desirable to control the amplitude at primary resonance. This is because the broad range of exciting vibrations generally means they extend down to the natural frequency. The intrinsic damping in the rubber can be more effective than a noise stop pad commonly inserted between coil springs and the structure. Moreover, the lower active mass of the rubber bearings gives a broader frequency range of good isolation. Steel bearings require supplemental damping devices to reduce the impact of spring resonance at higher audible frequencies. Rubber, however, has much higher intrinsic damping, so does not require any additional devices. In a paper titled A Comparison of Rubber and Metal Springs for Vibration Isolation, Dr. Alan Muir concludes, "The dynamic properties of rubber and the tendency for rubber springs to be less massive than equivalent steel springs lead to a somewhat wider frequency range of good isolation for rubber as opposed to steel springs. Once installed, steel bearings require adjustments by engineers so that they can perform as required under the load. This can be a time-consuming and sometimes costly process. More significant is the need for a space large enough to accommodate the engineer to gain access at the base of the building. For buildings with bearings sited in excavated basements, additional excavation must be completed to ensure that this space is made available. In comparison, rubber bearings do not require any routine attention after they have been installed. In fact, some are cleverly designed to allow remote pre-compression with self-releasing tie rods. As such, they eliminate the need for deep trenches for personnel access. The installation of an isolation bearing can fall victim to possible human error, which can have a colossal impact on performance in situ. However, rubber bearings are very tolerant to installation misalignment. Buildings such as concert halls or recording studios are considered the sole preserve of steel spring designs, but rubber is just as competitive and actually offers a number of benefits over steel. Steel shim plates that are placed inside a laminated bearing are fully encapsulated in rubber, which provides a protective barrier against corrosion, eliminating the need for maintenance. The large strains that natural rubber can accommodate mean that the material has a high energy storage capacity, which enables compact, space-efficient bearing designs. Rubber bearings can accommodate a certain amount of misalignment between the top and bottom mating faces and are relatively easy to install. Natural rubber possesses enough hysteresis to dampen resonant vibrations without the need for supplemental damping devices. Urbanization and infrastructure will continue to grow, causing ground-borne vibrations to increase. Choosing the correct product and material at the specification stage is vital. A modern building has a design life of typically 60 years or more, so it is essential to test each bearing to verify its stiffness characteristics and structural integrity before it's installed. Once in place, a bearing cannot easily be replaced or rectified. Natural rubber has a proven service life of more than 100 years. Elastomeric bearings are a proven technology, dating back to the 19th century. In the 1950s, laminated bearings made up of alternate rubber and steel layers were introduced as bridge supports. They were able to take up thermal changes in the length of the bridge without the maintenance problems associated with roller bearings. The Pelham Bridge in Lincoln, constructed in 1957, was the first application of this technology in Great Britain. The capability of laminated bearings to act as vibration isolation mounts for structures was first exploited in 1966. Albany Court is a block of flats constructed over St James's Park Underground Station in London. It is supported on 13 rubber bearings carrying loads from 60 to 200 tons. The success of the Albany Court project opened up the possibility of developing valuable inner-city sites for both residential and commercial use in locations near railways and roads. Thank you for taking the time to view our webinar. Our white paper, Building in Noise Reduction, is also available for download.